The biggest bug in the universe isn't in your computer, but in the fabric of reality itself. This glitch literally broke Einstein. He could not accept that a particle is a piece of a cosmic puzzle, not just a tiny ball. Here is why. An electron is a total drama queen. It lives as a wave of pure possibility, existing in many places at once. Look at it and it snaps into a single point. Reality has stage fright. Science calls this the measurement problem. We call it the deepest glitch in the simulation. Nobody, not even the guy who cracked spacetime, could explain why observing a particle forces its location. That is the mystery. So what is this undecided state? Physicists call it superposition. Fancy word for a simple glitch. Imagine a coin not just flipped but stuck midair. Spinning. Is it heads or tails? Yes, it is both, all at once. The particle cannot be bothered to pick a lane. Meet the mascot of this madness, Schrödinger's cat. This is not a real cat. It is a character in a thought experiment, the ultimate multitasker. Normal cats sleep 18 hours a day. A quantum cat. It juggles two realities simultaneously, dead and alive. The box is closed, so the universe has not decided yet. A classical cat has one life. Your grandma's cat has one life. A quantum cat, 9 lives is not a metaphor. It is mathematics. Here is the concrete substance. Superposition is not magic. It is the default setting. An electron does not pick a location until it must. A photon does not pick a spin until measured. But this creates a massive problem. If particles are this indecisive, why does our world look so solid? Why do we only ever see a living cat or a dead cat? The moment you open the box, the glitch ends, the coin lands. This raises the million-dollar question. What counts as a look? Does the universe need a conscious observer? Or does the wave collapse when a rock interacts with the box? That is the measurement problem, the deepest crack in reality. If you are feeling brave, we go deeper in the next chapter. So what happens when you force a particle to make up its mind? That moment is wave function collapse, the most violent jump in nature. 1 second the electron is a cloud of options, the next it is a single point. Every other possibility vanishes. Reality picks a lane and floors it, but here is the concrete problem. This collapse never appears in the equations. The math describes a smooth, fuzzy wave. It does not explain why the wave suddenly shatters into one outcome. That is the measurement problem. Compare this to your everyday world. Your coffee mug is not a blur. It is right there, solid and boring. But zoom in to the quantum level and you find a sea of indecision. Photons refusing to pick a path. Electrons living as fog. So how do we go from fog to coffee? How does indefinite become definite? The only answer so far is the word measurement, and that word is doing a lot of heavy lifting. This is where the question of the observer gets personal. You see, a measurement is not just a human staring at a screen. A measurement is any interaction that forces a choice. A photon hitting a detector. An air molecule bumping into an atom. But here is the twist. If every interaction counts, then collapse happens constantly. The universe is always deciding, which means the fuzzy quantum world never really exists on its own. It only lives in the gaps between measurements. This is the deepest crack in the foundation of physics. Some scientists say consciousness triggers collapse. Others say the wave never collapses at all. And a third group says we are misunderstanding reality itself. So who is right? That is the war. And in the next chapter, we meet the man who said the universe only exists when you watch it. But first, answer this in the comments. Do you think the moon is still there when you close your eyes? So we have a problem. The math says superposition. The world says definite. The Copenhagen interpretation offers an answer, and it needs a new character. Meet the observer, not you staring at a screen, not a detector. This is a cosmic director with a megaphone. Here is the scene. The quantum system is an actor in rehearsal. It runs every possible line at once, every emotion, every gesture, all at the same time. Then the director shouts action. The actor must pick one role, one position, one momentum. That is the measurement. The wave function collapses. The performance ends when the curtain falls. The audience sees one reality. Everything else vanishes backstage. Copenhagen says this is how the world works. The wave function does not describe what is real. It describes what we can know, and the act of measurement forces nature to make a choice. You do not discover reality. You force it to pick a lane. Now here is the feud. Physicists argue constantly over who gets to be the director. Is it the measuring device, the photon, the air molecule, the cat? Copenhagen says the observer must be a classical object. But it never defines where classical begins. So you get the greatest joke in physics: two physicists in a room. Each insists they collapse the wave function, but the moment they started arguing, reality had already collapsed. So they are too late. They sit there debating in a world that was already decided. Perfect. Takeaway: the Copenhagen interpretation works. It predicts experiments perfectly, but it leaves a gaping hole. Who is the observer? The universe stays silent. So here is your cue, your turn. Who gets to shout action? In your universe, drop it in the comments, and get ready, because in the next act, we meet the man who said the universe does not exist unless you watch it. That man was Hugh Everett, and his answer to the measurement problem was not that the universe needs a watcher, it was that the universe doesn't need to make a choice at all. Every possibility happens. The wave function never collapses. It just keeps branching. Here is how it works. Take the double-slit experiment. An electron approaches two slits. In Copenhagen, it picks one when measured. In many worlds, the universe splits. One electron goes left, one goes right. Both exist, both are real. You only see one because you, the observer, split too. Think of it as a cosmic choose-your-own-adventure book. You reach a decision point. Turn left or turn right. In Copenhagen, you pick one and the other vanishes. In many worlds, the book physically splits into two copies. You take one path, your alternate self takes the other. Both books sit on the shelf. Both are equally real. Now revisit Schrödinger's cat. In Copenhagen, the cat is both alive and dead until you open the box. In many worlds, the box opens and reality splits. The cat is alive in one branch and dead in another. You, the observer, split as well. When you seize a live cat, the other sees a dead cat. Neither outcome is privileged. This interpretation has a massive cost, infinite universes, but it completely removes collapse from the equations. The wave function evolves smoothly forever. No special observer needed. Now here is the payoff. Somewhere out there is a version of you that made every different choice. You took the job you turned down. You moved to the city you avoided. So if you ever feel regret, remember, in another universe you are living that life right now. Maybe they are richer, maybe they are not. But every version of you is still out there. So here is the question. If the universe splits at every quantum event, how many versions of you are watching this video right now? And how many of them have already hit subscribe? Drop a comment about what your alternate self might be doing instead. But many worlds is not the only game in town. And for some physicists, infinite splitting universes is a deal breaker. So they have proposed other ways to get from the quantum fog to the solid world you are sitting in. Start with decoherence. Decoherence says the wave function never collapses. It just loses information to the environment. Imagine screaming a secret into a stadium full of fans. The words scatter across thousands of eardrums. The secret still exists. But no one can reconstruct it. That is decoherence. A quantum system interacts with a photon, a molecule, a grain of dust. The superposition information bleeds out into trillions of particles. To you, the superposition disappears. But really, it has just been diluted into a universe of noise. Decoherence explains why we do not see cats that are both alive and dead. It does not explain when or why reality picks a single outcome. It just moves the mystery from the particle to the air around it. So we still need collapse. Step forward, Roger Penrose. He blames gravity. His orchestrated objective reduction theory says that when a superposition reaches a certain size difference in spacetime curvature, it collapses on its own. No observer required. The wave function just snaps, and the mechanism lives inside tiny structures in your brain called microtubules. Penrose thinks these microtubules can sustain quantum states and that their collapse produces conscious experience. It is elegant, it is speculative, and it has not been proven. Then there is the interpretation that puts you center stage. The von Neumann-Wigner idea: consciousness causes collapse. The wave function stays spread out until a conscious mind perceives it. No consciousness, no definite reality. It is philosophically neat. It also makes you the creator of the universe every time you open your eyes. Most physicists treat it as a thought experiment, not a working theory. So which is it? The environment steals the information. Gravity twists the wave function until it breaks. Or your mind forces the universe to choose. The debate is still alive, and quantum mechanics keeps its deepest secret. Here is today's question. Which of these explanations sounds the most plausible to you? Decoherence, Penrose, or consciousness? Drop a comment below. So here is the real question. If quantum mechanics is fundamentally random, do particles have free will? No, randomness is not choice, it is just cosmic dice. A particle does not deliberate between left and right. It got lucky. Real free will requires intention, not chance. Some argue the brain might amplify quantum indeterminacy into genuine decisions, but random noise does not make you free. It just makes you unpredictable. Now for the joke. Imagine your dinner choice is a quantum superposition. You are both craving pizza and tacos until you look at the menu and collapse the wave function. Is that free will, or just a measurement problem? If you picked tacos, was it you who chose, or did the universe randomly pick a branch for you? This is where the philosophy gets sticky. If consciousness causes collapse, your mind literally sculpts reality. Every observation is a creative act. But if many worlds is true, then every possible choice happens across branching timelines. You experience one branch, but your other selves live the alternatives. Your feeling of choosing might just be the path you ended up on. Quantum mechanics does not resolve free will. It replaces absolute determinism with absolute randomness. Neither gives you freedom in the traditional sense. But the fact that the answer is not settled means the mystery is still alive. So next time you make a decision, big or small, remember, you are participating in a quantum process. Whether you are collapsing a wave function or splitting the universe, your choice matters enough to shape reality. Now here is your quantum experiment. Comment below, pizza or tacos. But before you type, ask yourself, was that decision truly yours, or just the universe making up its mind? While you wrestle with the philosophy of your last meal choice, physicists are putting quantum mechanics on the witness stand. In 2018, the Big Bell test enlisted over 100,000 human volunteers to generate random bits, closing the freedom of choice loophole once and for all. The verdict, entanglement is real. Local hidden variables are dead, but the measurement problem, it got a mistrial. Collapse models are being tested directly. Experiments send massive molecules through interferometers to see if they decohere faster than quantum theory predicts. Others hunt for spontaneous radiation that collapse theories require. So far, nothing. If there is a collapse mechanism, it is hiding flawlessly. Now look at quantum computing. It is the ultimate exploitation of this mystery. Qubits exist in superposition, exploring many paths at once. Entanglement ties them together for computational speedups that classical machines can only dream of. But at the end of every algorithm comes the same wall: measurement. You read the result, and the superposition vanishes. The computer cannot tell you why. It uses the weirdness without understanding it. That is like debugging the universe's source code. You can run the program perfectly. The functions for superposition and entanglement work without errors. But the measurement event, the part that outputs a single reality, is written in some forgotten language. Maybe we need a cosmic programmer to clean up the documentation. The experiments keep coming, the superposition keeps spreading, and the measurement problem keeps its silence. The quest is still in its early stages. After a century, the measurement problem is still unsolved. So now it's your turn to decide. Which interpretation blows your mind the most? Copenhagen, many worlds, or something else? Drop your vote in the comments. Your choice might just collapse the wave function of this video's success. And if you want more mind-bending science, smash that like button, hit subscribe, and ring the bell. The universe may be random, but your support is exactly what we need to keep exploring.